Welcome to the lecture on resolution. We'll begin this lecture by looking a little bit at scales and then move on to resolution. There's obviously a connection. The main focus is on resolution, but let's just get some terms connected to scale out of the way with first. So when we talk about scale, we have this unfortunate business of there being two uses of the word. The more sort of data scale definition, where you may have seen this slide before. We have things like the nominal scale, where we name things, objects, they are described using words perhaps. The ordinal scale here, where we can just put things in a particular order. We don't specify how big they are, the distances between these objects. They just have a particular rank, a particular order. The next scale we can talk about is the interval scale, where there are known steps between the different levels. What these levels are doesn't really matter, essentially, but there is a fixed number of steps, or there is a fixed distance between one level and the next. This can be discrete or continuous, but the distance we travel for any particular measurement is always the same. But there's no true 0 point in the interval scale. We can use functions such as addition and subtraction, but we can't multiply. So the standard example is that 20 degrees C is not twice as warm as 10 degrees C. But the distance between 0 degrees C and 10 degrees C is the same distance as between 10 degrees C and 20 degrees C. And then we have the ratio scale, where we actually have a proper 0 point, so we can now divide and multiply. And of course the ratio scale as well can be discrete or continuous. So this is the idea of scale. There is a connection to resolution in a very tangential way, perhaps, in that we can specify the distance between the different objects in greater detail as we move to the right along this, ignoring this right-hand image, or the right-hand column, sorry. We use the word scale here, and the reason I'm bringing this up is because of this slight connection. We might see the similarities in what we're talking about between scale and resolution, and even data scale here. But let's move on. So let's look at map scale. The map scale is when we, for example, we have one unit on the paper. A map represents usually a larger number on the ground. And certainly in terms of GIS, it's going to be a larger number. And so 1 to 1000 means 1 millimeter on paper represents 1000 millimeters on the ground, if we have a 1 to 1000 scale. Well, that's good. So if we bring in something called acuity, which basically means what's the smallest thing that we can see, the thing being something, any object, a symbol on a map perhaps. Well, standard measurements say that at arm's length, sort of about 46 centimeters, we can see something as small as 0.15 millimeters. That's an object. It's a little different for distances between objects, but that's a more advanced topic. Let's just stick to this for now. So 0.15 millimeters at arm's length, so a sort of typical reading distance perhaps for when you're reading a map or a drawing, some sort of illustration. So if we then use our map scale, if we have a 1 to 1000 map, 0.15 millimeters times 1000 would then give us 150 millimeters, or 0.15 meters in reality. So the smallest thing that we can represent on a map at a scale of 1 to 1000 would be 0.15 meters big. Typically, though, our maps are not quite so detailed. The 1 to 1000 you might find perhaps in a drawing, but on a map, more likely we've got a different scale. 1 to 50,000 is quite common for a lot of maps that we use, and even other scales come in there. And if we apply the same formula here, 0.15, the smallest object we can represent on the paper, multiply that by 50,000, well, we can see that the smallest possible object that we can represent on a map then becomes 7.5 meters. We've suddenly got a much larger object. Details start to disappear here, perhaps, when we're talking about scale. And just to clear a couple of things up here, large-scale maps, small things are made large. So we take what's, for a large-scale map, we take a small area and we make it big. Whereas a small-scale map, we've got larger things, continents, entire countries, continents, that sort of thing, and we make them small so we can see them. It's the opposite way around, perhaps, to how we imagine large and small scale in everyday language use. But if we can just try and remember these things when talking about maps, that's good. The confusion is very understandable. But the main focus of this lecture is, as I say, resolution, but it felt necessary to bring in a quick discussion about scale, just so that we've got that cleared up, because obviously there is a relationship here. But let's get moving on to resolution. So we need to talk about something called the Nyquist rate. Basically, what is it that we can see? How small an object can we measure? Well, this of course depends on how we measure, what instrument we're using to measure with. And here in the figure we have this waveform, this sine wave, typical thing. Usually we're applying this concept to something that is periodic, like a waveform. In this sense, it's got a period, it repeats again and again. But we also apply it to objects that don't necessarily repeat. We can apply this just to the change from one state to another. How quickly can we, or what is the rate or the area over which we can measure that change from one thing to another? We'll try and illustrate that a little better here. So if we do this measurement in time or space, so this could be something that varies in space, say, so you have some geographic feature that you think repeats, or quite often we apply this to signals in the electromagnetic spectrum, light or sound, which isn't electromagnetic, but it also follows a waveform. And if we set up our measuring device so that it measures at this particular periodicity, measuring like this, we can capture the peaks and troughs of this waveform perfectly, and we can recreate the signal then. Whatever it was that was creating this signal, we can recreate it. So we say we've measured here, we've measured there, we've measured up here, we've measured down there. So we've captured the peaks and the troughs accurately. And then we are also making an assumption about the shape of the wave. That we have to remember. We're assuming that it's going to be a sine wave in order to fully recreate the wave. So we've captured information. We haven't captured everything, but we can recreate the signal accurately enough. But what happens if we're not actually on the peaks and troughs? You know, if our measuring is shifted somewhat, we don't start or place our first measurement at exactly the beginning of the signal or the first peak or the first trough. Well, it still works. We can still capture the general waveform. Once again, we're doing this using the extra information of what we think the wave looks like, or how it will vary, but we capture the periodicity of that function, that wave, that signal, that object. So we can do that accurately enough so that we can recreate it. So we've measured it. That was when we're measuring. We've set up our device, and it can measure with a particular frequency. Our measuring in time or space. So if we then measure something with a lower frequency, so we're measuring something that is larger, so to speak. Well, that's fine. We can do that. We actually managed to capture enough information, again using some assumptions about what the waveform looks like. We can capture the information we need to recreate that signal. So we've managed that. So here we have a sampling distance or frequency that is smaller than the periodicity, the wavelength of the thing we're measuring. So we've got a higher resolution. There we go. Whereas if we then measure something that varies more rapidly over a shorter distance, shorter time than our measuring device, then we don't capture all the information necessary. Even with the knowledge of this being a sine wave, we are not actually capturing all the variation that's happening here that we need to recreate the signal. And what we actually end up with can potentially, in the worst case, look like the lowest frequency signal that we've captured, just because we've missed the transitions from rising to sinking again, or the change in the signal, whether it's increasing or decreasing. So we don't capture all the detail. If we have some more information, we might perhaps be able to recreate the higher frequency signal, but that will require some assumptions or other information that we can put into our modeling of the original signal. But that really, you cannot increase the resolution of the signal that much without making assumptions or adding extra data from some other source. So we really need to be measuring at a fast enough rate, or with a high enough data density in order to capture the signal. It needs to be what we generally speaking with half the distance, we say, of the wavelength in order to capture it. So that's the Nyquist rate. Nyquist, Swedish American, so we'll call him Nyquist rather than Nyquist. We have this minimum size that we can't go below to meaningfully capture data.